Hello, and welcome to Backer Breaks It Down. In this episode, we are looking at the short-run behavior of polynomials, and we are going to interpret a polynomial function completely. So we are going to focus also on end behavior, okay? But we're going to look at, like, if we're given a polynomial function formula, how can we analyze and interpret it for all of its behavior? So let me remind you of these things, because the truth is we have done this. We're just putting it all together in this lesson. So when it comes to the long run, which is the end behavior of a function, we need to determine the leading term of the polynomial, and then we can use our leading term test. Now you may need to go back and look at the leading term test in an earlier lesson. 11.2 is where we did leading term test. But perhaps you have it memorized. That makes it easier for sure. Anywho, short run behavior is predicted from the zeros given by a linear factor. However, not all of our factors are going to be linear. We are going to use the zero product property, so we are going to set the factor equal to 0 and solve. We may need to use the quadratic formula for quadratic factors that can't be factored further. And then lastly, we have our constant, which is our y-intercept. And the y-intercept of any function can be found by evaluating f of 0. So that means plug in 0 for x and calculate. So let's take a look at such a problem. Check out this baby. So we have the function f of x equals 5 minus 2x times the quantity x squared minus 10 times the quantity 2 plus 4x minus x squared. Oh my goodness. This is already in factored form. Okay, so let's analyze it for its degree, leading coefficient, constant, and end behaviors. Let's get that out of the way. That's quick and easy to do. For 4 of those things, I need to be like, well, what's the leading term? So remember, leading term, I want to look at each factor. I want to be like, what's the leading term of that factor? I also want to consider any outside multiplicity, right? So the first factor, 5 minus 2x, has a leading term of negative 2x. The next factor has a leading term of x squared. And the last factor, 2 plus 4x minus x squared, has a leading term of negative x squared. So one thing that's a little misleading is when we hear leading term, we think it has to be the one out in front, and that's not the case. It's the one that has the highest degree. So I have 3 leading terms. So what I need to do is I actually need to multiply all 3 of these leading terms together. And this will give me the leading term of the entire polynomial. So if I just consider the numerical coefficients, I've got negative 2 times a negative, right? And so that's going to give me positive 2. And then x to the first times x squared, I'm going to add the exponents, and I'm going to get x to the 5th. So that we're looking at a degree 5 polynomial. The leading coefficient is 2. So I would describe this as being odd because of the degree, and then the leading coefficient is positive. And odd positive polynomials have an end behavior on the left of negative infinity and on the right of positive infinity. Now when it comes to that constant, remember the constant is the y-intercept, okay? And I can find the y-intercept of any function by plugging in 0 for x and calculating. So this would ultimately be 0, this is 0, this is 0, this is 0. Or I can plug that whole thing into my calculator with zeros. But really what it comes down to is 5 times negative 10 times 2. So my constant would be negative 100. But like I said, just throw that into a calculator, let it figure it out. Okay, so now let's talk about these roots or these zeros or these x-intercepts. All right, so I'm going to use my zero product property. So I'm going to take each factor and set the factor equal to 0 and solve. So starting with that first factor, like this one I could probably do mentally. So if I did like 5 minus 2x equals 0 and I solved for x, I would have like negative 2x is equal to negative 5. So that means x is equal to 5 halves, or 2.5. So that's one of my zeros. Taking a look at my next factor, we have x squared minus 10. And I say use the square root property with this one, right? So I'm going to take the factor x squared minus 10, and I'm going to set it equal to 0. And so, yeah, it makes sense to use the square root property. So I isolate the quadratic expression by adding 10 to both sides, and then I take the square root of both sides. So I get that x is equal to positive and negative square root of 10. And that is positive and negative 3.16. I'll just write that over here. And then for our last factor, we have 2 plus 4x minus x squared. Now, I mentioned earlier that this has been factored completely, so I cannot factor that further. So I'm going to have to use my quadratic formula in order to figure out what the zeros are here. So I need to identify my ABCs. A would be negative 1 because it goes with the quadratic. B would be positive 4, and C would be 2. And I'm going to plug those values into my quadratic formula. So this is going to get to be a little bit messy. So I'm going to come down here and I'm going to be like x equals, and I have negative b, so negative 4, plus or minus the square root of b squared, so 4 squared, minus 4 times a is negative 1, times c is 2. And this is all divided by 2 times a, so 2 times negative 1. Now, I am a perfectionist, so I usually figure out, like, what is this inside the square root before I do, like, any decimal calculations. So I would have, like, negative 4 plus or minus the square root of, calculate that, use your calculator, you get 24, and this is all over negative 2. So now all that's left to do is to calculate the two results from this. Now it's everything on top divided by negative 2. So when I go negative 4 plus the square root of 24 divided by negative 2, I get negative 0.45. And when I minus on top, I end up with positive 4.45. And so those are all my roots and zeros. I have a total of 5 of them, which is fitting considering like it was a degree 5 and I didn't have any like multiplicities greater than 1. So I would have 5 different zeros, okay? But that's how we analyze or interpret a polynomial function. So the long run end behavior, we're identifying the leading term and using our leading term test. The short run behavior, we can find the zeros by setting the factor equal to 0. We may have to use quadratic formula or square root property. And then the constant, that's the Y-intercept, and you can find that by evaluating f of 0. And that's how Becker breaks it down.